Hello students, welcome you all to the next session regarding discussion of air standard cycles, a continued part. So in the previous sessions, we have discussed regarding how to calculate the thermal efficiency of an Otto cycle as well as mean effective pressure of an Otto cycle. In this video lecture, students, we will be discussing regarding how to calculate the thermal efficiency of a diesel cycle. So already on the screen, you can see that my email IDs are available to you. So if you have any queries at any point of time, you are free to send me an email to this following mail IDs which are available on the screen, as well as message to my WhatsApp number also. Okay, students. So now let us begin with the discussion of today's session, that is how to calculate thermal efficiency of an diesel cycle. So initial students, already we know that diesel cycle is a cycle where in the suction stroke only air enters, and at the end of the compression stroke to the compressed air, the fuel droplets are injected, due to which the ignition process begins. Because of this principle, that is using the compressed air itself, we call those engines as compression ignition engines. So when the fuel droplets are sprayed inside the engine cylinder, the heat addition which takes place, it takes place at a constant pressure process, and here there is high pressure air, so that the fuel ignites spontaneously and the combustion process begins. So as a result, for the diesel engines, as the heat addition takes place at a constant pressure process, we even term it as the diesel cycle or constant pressure heat addition process. So like the Otto cycle, students, here also the remaining three processes, that is isentropic compression, isentropic expansion, and constant volume heat rejection, they remain the same even for the diesel cycle. So just once again I am repeating, students: isentropic compression, isentropic compression, process 1 to 2, it is the same even for the diesel cycle as that of the Otto cycle. Then process 3 to 4, that is isentropic expansion, it is also the same here also. And the third process, that is constant volume heat rejection, it is also the same here also. It is constant volume heat rejection. So the three processes of the Otto cycle, they are again repetitive in the diesel cycle. Only the process which is going to change is the heat addition process. Here the heat addition takes place at constant pressure heat addition. So except that, other terms remain the same, students. Then very important point, as I said, when I begin to draw the PV diagram of an Otto cycle, it somewhat looks like this, students. Please observe here. Just I will draw the pressure volume diagram. So this is this one. So initially 1 to 2, what happens? Isentropic compression. So this is point 1. Process 1 to 2. Then here heat addition takes place at constant pressure, students. So you can see here, constant pressure means a horizontal line. You can see this is 2 to 3, constant pressure heat addition process. Then, students, isentropic expansion, it will somewhat like this, 3 to 4. And finally, students, heat rejection at constant volume. See, so if you observe carefully, only the process 2 to 3, it is different when compared to the Otto cycle. except that remaining processes 1 to 2, 3 to 4 and 4 to 1, they are the same even for diesel cycle like the Otto cycle. So this is the nature of graph for the diesel cycle, students. Similarly, if you observe the TS diagram for this one, please observe how does the TS diagram look here also. That also we shall discuss here. Temperature versus entropy. Both the graphs are important from the examination point of view. Each graph is having 1 marks, 2 graphs, 2 marks will get very easily. So the first process I said, students, it is isentropic compression. Isentropic compression means entropy remains constant. Please observe here. How does it look? See, this is process 1 to 2. Then from here, heat addition takes place at constant pressure. Somewhat it looks like this. 2 to 3. Then isentropic expansion 3 to 4. Finally, heat rejection at constant volume. So if you see the curve, it is like this. So it is somewhat like this, students. 1 to 2, 2 to 3, 3 to 4, and finally 4 to 1. This is the TS diagram. So which already I have drawn, you can see here. So for each curves, we need to do the labelings. Then only the examiner will understand what is the indication of each curve. So if you observe carefully, these two processes 1 to 2 and 2 to 3, 3 to 4, they are isentropic processes. I have named it as PV to the raised to the power of gamma is equal to C. Similarly, students, 2 to 3, it is constant pressure addition process. You can see here I have written P is equal to C. Similarly, 4 to 1 constant volume heat rejection process, I have shown V is equal to C here, you can see. And the heat addition takes place at constant pressure. You can see here I have written QA and I have shown the arrow mark flowing towards the process 2 to 3. It is heat addition process. Similarly, heat rejection moving away from the diagram. You can see I have shown here QR. The same things I have repeated even for the TS diagram. So as it is an isentropic process, I have shown here S is equal to C. You can see here both 1 to 2 and 3 to 4. Then this is P is equal to C, 2 to 3, as well as 3 to 4, 4 to 1 is V is equal to C. I have shown the heat addition and heat rejection processes. Now, so always, as students, to calculate the thermal efficiency of an diesel cycle, we need to find out the heat transfer of processes, heat transfer equation for all the 4 processes. Let us begin now. Initially, the first process is which one? It is with respect to the process 1 to 2, students. That is this one, isentropic compression process. So for the isentropic compression process, the air is compressed isentropically, and as it is a reversible adiabatic process, for this one, the heat transfer, students, you know that the adiabatic process, heat transfer is 0. That is Q1 to 2 is equal to 0. Then process 2 to 3, students, this is it is, you can see here. So here heat addition takes place at what process? Constant pressure process. So for 2 to 3, we are writing it as heat addition. Q addition is equal to Q to 3 is equal to MCP, because heat addition takes place at constant pressure. MCP T3 minus of T2. This is the heat transfer equation for the second process 2 to 3. Then students, when we come back for the next process, that is from 3 to 4, students, again it is an isentropic expansion or reversible adiabatic expansion process, which means for this 3 to 4 process, the heat transfer Q3 to 4 is 0. And the last which we are left is with the process 4 to 1, students, that is a constant volume heat rejection process. So here the heat rejection is done at a constant volume process. So we write it as Q R is equal to Q41, that is MCV T4 minus T1. T4 minus T1. This is the heat transfer equation for the fourth process. Now what we will do is we will write the thermal efficiency equation for the given diesel cycle. So thermal efficiency equation, students, how do I write generally? Thermal efficiency equation is given by Q addition minus Q rejection whole divided by Q addition. So in this process we have seen Q addition takes place at process 2 to 3, rejection takes place at 4 to 1. So those equations I am going to write now here. That is Q addition minus Q rejection by Q addition. So the heat transfer equations I am going to write here. So if you observe now carefully, students, here the mass of air is common everywhere, it gets cancelled. Then what I will do is I will take the Cp T3 minus T2 to the other side, which means on simplification my equation becomes like this: 1 minus Cv into T4 minus T1 by Cp into T3 minus T2. Then this Cv, students, I will transfer it to the denominator part. So if I transfer it to the denominator part, what do I get? I get Cp divided by Cv, which is a thing, but it is a ratio of a specific heat, which is represented by the symbol what? Gamma. So now please do observe here. Yes, this I get the equation 1 minus T4 minus T1 by gamma T3 minus T2. Now what I need to do, students, here is all the temperature limits, that is T4, T3 and T2, I want to write them in terms of temperature limit T1. So for that, what I'm going to do is, for all the other processes, I will be applying the PVT relations in such a way that I can convert the value of T4 in terms of T1, T3 in terms of T1, as well as T2 in terms of T1, so that the final equation I get only in terms of the compression ratio RK. Here a new term arises, students, known as cutoff ratio RC, as well as expansion ratio RE. What are those cutoff ratios? Please observe here, students, on this on the PV graph. So if you observe from 2 to 3, whatever the volume ratio we take from 2 to 3, we call it as cutoff ratio, that is RC is equal to V3 by V2. This is known as cutoff ratio. This is cut off ratio, cutoff ratio, that is V3 by V2. Similarly, students, from 3 to 4, whatever the volume ratios we are going to write now, we call it as expansion ratio, students. That is, please observe here, expansion ratio. Expansion ratio, that is RE is equal to V4 by V3. V4 by V3. So already you have learned regarding compression ratio. Compression ratio, it is from 1 to 2. We write it as what? RK is equal to V1 by V2. So the final equation of thermal efficiency will be writing in terms of compression ratio, cutoff ratio, as well as expansion ratio. Let us see how we are going to write that one. So now, as I said, gamma is equal to Cp by Cv, that I have replaced in the equation number 1. From PV graph beginning, I am considering the isentropic process compression ratio RK is equal to V1 by V2. Cutoff ratio, students, as I said, V3 by V2. Then expansion ratio V4 by V3. Then I can connect all these three ratios together in a single relation. What is that relation, students? I can write this relation in this form also, students. That is compression ratio RK as the product of cutoff ratio RC with the expansion ratio RE, or RE is equal to, I can term it as RK divided by RC. This is a common relation. So therefore, you can see here, I have termed it as expansion. So I can write it as RE is equal to RK by RC. Now students, for the isentropic process 1 to 2, I am writing the temperature volume relation, that is T2 by T1 is equal to V1 by V2 raised to gamma minus 1. So what is V1 by V2? So here you can see here, it is V1 by V2, something what it is? Compression ratio RK. So I can write this expression as what? T2 by T1 is equal to RK raised to gamma minus 1, or T2 is equal to RK raised to gamma minus 1 into T1. This is for the first one. I have written the value of T2 in terms of T1. Then moving for the second process, 2 to 3 students. So 2 to 3 is what? It is a constant pressure process. So for constant pressure process, what is my PVT relation generally? So general PVT relation, how do I write? I write like this: P2 V2 by T2 is equal to P3 V3 by T3. So 2 to 3 is what? It is a constant pressure process, students. So what it means? My PVT relation is V2 by T2 is equal to V3 by T3. Or what I can write, students? I can write it as T3 is equal to V3 by V2 into T2. Already the value of T2 I have written in terms of T1. I can replace that value here, T2 in terms of T1. And V3 by V2, students, as I said in the graph, it's a new type of ratio. We call it as what? RC. So now those things I am going to substitute here. That is T3 is equal to T2 RC, because this is the volume ratio is representing the cutoff ratio RC, and T2 value just now I have written here T1 into RK raised to gamma minus 1. So what does it mean, students? So I can replace the value of T3 in terms of T1 itself. That is T3 is equal to T1 RK raised to gamma minus 1 into RC. So I have got T2 in terms of T1, T3 in terms of T1. Now which is left? Only T4 is left. For that, I'll consider the process 3 to 4 students. So it is a isentropic process. For this, the temperature volume relation, which I am going to write, it looks like this, students. That is T4 by T3. T4 by T3 is equal to T4 by T3 is equal to T4 by T3 is equal to V4. Sorry, it should be V3 by V4 raised to the power of gamma minus 1. Because 0 to 4 is which process? It is adiabatic process, reversible adiabatic process. So I can write it in this form also, students. That is T4 by T3 is equal to V3 by V4 raised to the power of gamma minus 1. Now, if you observe that, I can write as T4 is equal to T3 into V3 by V4 raised to the power of gamma minus 1. Here, what I can do, students, I can make a small simplification or alteration. What you can say, what I am doing here is I am multiplying this equation by V2 as well as I am dividing. You can see here. So no change, students. If it gets cancelled, if these terms gets cancelled, again you are getting the same form V3 by V4. So why I am doing this method? Please observe here. V3 by V2, if I write here, I can write it in terms of what? Cutoff ratio RC. Similarly, now observe here, students, carefully. This is what? V4. What is process 4 to 1, students? Process 4 to 1, if you observe on the PV graph, it is a constant volume process, which means V4 is equal to V1. So in this particular expression, students, can I replace V4 as V1, which means what does it become? It becomes V2 by V1, which means it comes in the form of compression ratio, that is 1 divided by RK. So to get the T4 equation in terms of the cutoff ratio and the expansion ratio, compression ratio, I am multiplying and dividing by V2. So now please observe here, I have done those things. I have replaced V4 by V1 as process 4 to 1 is a constant volume process. So therefore, what do I get here? The value of T3, students. This is the value of T3. Yeah, whatever you can see here, this is the value of T3, which already we have determined. That is T1 RK raised to gamma minus 1 into RC is the value of T3. Now, V3 by V2. V3 by V2 is what? It is RC. This I have written here, students. This I have written here, RC. Then in the denominator, what I have got? I have got in the denominator as, say, it is nothing but V2 by V1. V2 by V1, I can write it in this form also. That is 1 by V1 upon V2. Like this. So it is from here, this particular expression. And what I can write this one I can write it as 1 by R suffix K. So on simplification, my equation number 5, how I can write? I can write it as RC by RK to the power of gamma minus 1. And finally, these values, that is T4, T3, and T2, I'll substitute in my thermal efficiency equation. On substitution, if you see, I get it in this form now. So what are the common terms? If you observe carefully, T1 on denominator as well as denominator, it gets cancelled. And if you observe carefully, I have got the equation only in terms of the cutoff ratio RC and compression ratio RK. So now my equation, students, finally on simplification, what do I get? I get it is in this form, that is 1 minus 1 by RK raised to gamma minus 1 into RC raised to gamma minus 1 by gamma of RC minus 1. This is the thing, but the equation for thermal efficiency of a diesel cycle. So this is the method, students. We need to follow the steps. Only the very, very important thing you need to remember is all the temperature terms, that is T2, T3, T4, you need to write in terms of T1, such that the final expression when you are writing, it should consist of only the cutoff ratio RC, compression ratio RK, and ratio of specific heat gamma. So this is equation number 6, the final expression for the thermal efficiency of a diesel cycle. Thank you, students.